Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistants. And today we are looking at rates of reaction, specifically rate expressions. They're very simple to do. Just follow along as I perform the function on these two examples that I have here today. So the first one asks us to write the rate expression for the following reactions. Very simple process. You're going to have the right-hand side, which is going to be increasing as the reaction proceeds, and the left-hand side, which is decreasing as the reaction proceeds. And that will inform on how the rate expression is going to look. So we're going to have your rate is equal to the 1 over 6 times the change in the concentration of CO2 over the change in time. That's for the first term. The reason it's a negative is because you have the CO2 is decreasing as the reaction proceeds. And the reason it's 1/6 is it's 1 over the coefficient. So this is also equal to, again, negative 1/6 times the change in concentration of H2O over the change in time. And those brackets, by the way, are indicating concentration. So this is also equal to positive 1 over 1, which we're just going to leave blank, change in concentration of glucose, C6H12O6, over change in time, which is also equal to positive 1/6 times the change in the concentration of diatomic oxygen, molecular oxygen, over the change in time. So that's our rate expression for number 1. Number 2, switch over to black for number 2. Number 2 is going to have rate is equal to negative the change in concentration for Cl2, molecular chlorine, over the change in time, which is equal to negative, again, because it's the reactant, negative 1 over 2 times the change in concentration for hydroxide ions over time, which is equal to positive 1 over 1, so we're just going to leave that as it is, change in concentration for chloride ions, so chlorine ions, which would just be chlorides, over the change in time, which is equal to positive the change in the chlorite ion over change in time, which is equal to the change in concentration of water over change in time. Okay, last one, number 3. We have rate is equal to negative 1/6 times the change in concentration of lithium over the change in time, which is also equal to negative the change in concentration of molecular nitrogen over the change in time, which is equal to positive 1/2 times the change in concentration of lithium nitride over the change in time. So that's all there is to it when it comes to rate expressions. All you're trying to do is say that the rate in which this reaction occurs is directly proportional to any given one of these terms, or is equal to any given one of these terms, which are all proportional to one another because they're all in the same equation. Let's look at something just a little more challenging. This is given the reaction presented here, and supposing that molecular hydrogen is being produced at a rate of 0.042 molars per second, at what rate is white phosphorus, which is that P4, formed, and at what rate is phosphine consumed, which is the pH3. So we know, what do we know from this information? Well, we know phosphine is a reactant, and we know that our white phosphorus and our molecular hydrogen are both products. So that's important, which means that we also know that the molecular hydrogen is being produced at a rate of 0.42 molars per second. So rate is equal to, in this case, delta H2 over delta T times 1 over 6. We know that to be a fact as part of the rate expression. However, we don't have the 1 over 6 component. All we know is that hydrogen is changing at a rate. So we know this delta concentration of molecular hydrogen over the change in time. So we know that if we were to complete this rate expression, let's go ahead and do that. It's equal to delta white phosphorus over delta T, which is equal to negative 1/4 times the change in phosphine over change in time. So that's our rate expression, and from that we can get everything else. So we know that our delta H concentration, our delta H2 concentration over delta T is being produced at a rate of 0.42 molars per second. So we know that that is 0.042 molar per second. Okay. We also know how to relate that to every other thing on our list. So we know that 1/6 of this value is equal to our white phosphorus. So all we need to do is we could say that for white phosphorus being formed, we know it's delta bracket P4 over delta T is equal to 1 over 6 times delta concentration of molecular hydrogen over change in time, which we know to be 0.042 molars per second. Which, if you do the calculation out, gives you approximately 0.007 molars per second. Okay. We can also calculate the amount of phosphine, or the rate at which phosphine is consumed, which would just have to relate our value right here to our value over here. So we know that if we were to set these equal to one another, 1/6 delta H2 over delta T is equal to negative 1/4 delta pH3 over delta T. Now we want to get this term over here by itself. So we're going to multiply both sides by -4. So we get delta pH3 concentration over delta T is equal to -4/6, which you can reduce if you are so inclined to 2/3. Just for the sake of simplicity and explicitness, I'm leaving it as 4/6 delta H2 over delta T, which we can then rewrite as, let's go ahead and reduce it now, -2/3 times our 0.042 molar per second. So if you do the calculation, you end up getting -0.028 molars per second. But it is asking at what rate is phosphine consumed. Now, if it was asking at what rate is phosphine changing, you could leave the negative. But when you're saying phosphine is consumed, you're kind of implying that it's the absolute value of whatever it is that you get. At the same term, you can look at the rate in which white phosphorus is formed. It's not asking for the change, it's asking for the rate at which it's formed. So that would be the absolute value. The absolute value of a positive is just a positive, but the absolute value of a negative is also a positive. So for this one, our actual answer is going to be positive 0.028 molars per second. And it's important to understand that distinction, just because if they're asking you that in those terms, they're looking for the rate at which it's consumed. If it's being consumed at a negative rate, that means it's being actually formed. So it's important to make that distinction. Again, you could leave the negative on if it was asking at what rate phosphine changes, or what rate the concentration of phosphine changes. But if it's asking if it's consumed, you just want to turn it into a positive.